before we get into more discussions concerning biology and functioning in biology, we really have to think about the underlying principles and mechanisms that make biology function. And first and foremost, we have to consider many of the biochemical or chemical processes that make biology what it is. So we have to look at simple chemical things like elements and atoms and compounds. We have to look at chemical bonds, and most importantly, in the long run, we have to look at water and the effect of water on different living organisms. So really in biology, chemistry is everything. When we look at what a cell does, it is everything based in chemistry. We have to look at matter, we have to look at energy, we have to look at things like what will this compound or drug do inside your body, right? What about those $150 beauty creams? What's that going to do? Does it do anything? These are all things that we have to consider, your interaction with the environment and what you're putting into your body. So when we look at chemistry, we often think about things like pharmaceuticals, we look at steroids, we look at things that are going to interact with our body and cause particular things to occur. But when we look at those pharmaceuticals or anything that you put into your body, we really have to know how it ties to water. And the reason we're so interested in water is we've talked before that we think all life evolved in water. We look at the idea that the living things that we know of require water in some form, either liquid or gaseous or ice. And we also look at the idea that in you, these chemical reactions that we're going to look at have to occur in cells that are 70 to 95% water. So we've got to take water into consideration anytime we talk about chemicals and processes in your body. And we'll come back to water later. When we look at elements and atoms and compounds, these are very chemical terms, right? Sure. Briefly, what we want to think about is what it actually means to be an element. So an element, we actually look at 92 different elements in nature. So those are 92 that we have to kind of deal with in biology. And what we're actually looking at is something that cannot be broken down And when I say that something that cannot be broken down, meaning that you can't break it down into another substance. An element is something we refer to as pure matter. So when we look at an element, every atom of that element has the exact same composition as all the rest. So many of you have probably seen this table before. This is the periodic table, of course, and I certainly don't think that you're going to memorize this. Please don't even try. But what I do want to think about is the elements that are going to be most important for our discussions. And I have them here in yellow for you. So hydrogen, carbon, nitrogen, and oxygen, phosphorus and sulfur. But we'll also look at things like potassium and calcium, sodium, lots of these. What we won't focus on much for you, of course, are helium and neon. These are not important things for you, but lots of these other things are. Even these ones here in the middle, iron, nickel, copper, zinc. No, you can't be exposed to these in large quantities, but these are what we call trace elements or trace minerals. And if you read the back of your vitamin bottle, they're all going to be there. So what elements are you actually composed of? What are the big elements that make up you? Well, I just told you a couple of them. What do you think? You have 25 elements that are essential to you. 4 of those 25 make up 96% of your weight. What do you think they are? Carbon, oxygen, hydrogen, and nitrogen. Those together in your body make up 96% of your weight. That's huge, right? Trace elements I mentioned to you: iron, fluoride. Some of you may be familiar with fluoride if you were on well water as a kid. Iodine. These are all things that we look at in your body that are actually going to be what we call later something known as coenzymes. These things are going to help your body work better, and we'll look at all of those. So like I said, these big 4. And then the remainder of this list make up a small percentage, but these are all really important anyway. And the trace elements down at the bottom make up an even tinier percentage. But these are all things that are essential elements for you. We've got to have them, okay? Now, when we look at a compound instead of an element, a compound is a combination of at least 2, sometimes more, elements. So when we look at compounds, we can think about things like H2O, CO2, right? NaCl, which is the one I have down here below for you, sodium chloride, better known as table salt. So we're taking sodium, the element, combining it with chlorine, the element, and getting table salt. The interesting thing about sodium chloride is sodium and chloride alone would be very toxic to you, but together they're a very tasty food additive, right? Amazing things in chemistry and how you interact with them. So when we look at these elements, they're made up of one kind of atom. We said that. Atom is this tiny little unit of matter that is made up of protons, electrons, and neutrons. When we talk about atoms, we have to look at charge. So what we want to know is this particle positive, negative, or neutral? And many of you know that protons are positive, electrons are negative, and neutrons are neutral. So electrically speaking. So when we put these together, what we want to look at is how they can actually interact then with other elements. So if we take something like helium, 2 protons, 2 neutrons, 2 electrons. So if you have two positives, 2 negatives, and you add them together, you get a neutral element, right? This is important. This is something we'll come back to later on. But you see there are these 2 electrons on the outside, and in the nucleus we have the protons and the neutrons. And so what we're going to think about when we talk about compounds primarily are these electrons. These will be the most important for us because they are what is actually going to interact with other electrons on other elements and actually form compounds. So we're going to have to kind of keep track of these elements as we go. Carbon is a much more common element for us to be dealing with for you. 6 protons, 6 neutrons, 6 electrons, fine. Everything balances out, great. It's an electrically neutral element, fine. That's fine. But what we're going to look at is the fact that we can actually change these number of electrons that we see in surrounding our nucleus of carbon. And so if we have carbon with its nucleus in the middle, we actually have a shell, an electron cloud or shell that goes around the outside. The first one is going to hold 2 electrons. The second, so 6 minus 2, gives us 4 electrons we need to put around the outside of that. Now, when we look more at compounds, we're going to look at the fact that carbon is okay with 4 on the outside, but he'd really like to have 8 on the outside. 8 electrons at the outside ring or outside cloud is preferred. So we have to figure out how we can get carbon to that point and how we can make him happy. But in the meantime, what we have to think about is that things change with these atoms. I mean, this is perfectly fine to think about this carbon atom in this way. We put a whole bunch of these carbon atoms together, we get carbon the element, fine. But when we look at changes in anything associated with neutrons, electrons, we're going to change this atom slightly. So what I mean is, if we take carbon, okay, we take carbon, and we said that it has 6 protons, 6 neutrons, 6 electrons. 6 protons is the only thing that really defines it as being carbon. What we can look at is if we change this number of neutrons, say I take carbon and instead of 6 I give it 7 neutrons. Well, it's still carbon. By definition, it has 6 protons. It's still carbon. But what we look at with these different neutrons is forming something we know as isotopes. Many of you know isotopes, or radioactive isotopes, from medicine, right? Well, let's look at a more simple one to start. Let's take hydrogen. Hydrogen has 1 proton, no neutrons, 1 electron. It is electrically neutral at this point. It would like to have 2 electrons in this outside shell because it only has 1 shell. That shell prefers to have 2 electrons. It has 1, but it's okay. It'll deal with it. We'll look at how it deals with it when we talk about compounds. But what we want to add to this is we start with hydrogen here. If we add 1 neutron, we get deuterium. This is an isotope of hydrogen. If we add another neutron, we get tritium, another isotope of hydrogen. These actually are all hydrogen. But what we have to look at is the fact that the mass or the weight of these atoms is actually changing. Why is it changing? So which of these would actually be the heaviest? When we look at using isotopes in medicine, we use them for things known as tracers. And essentially what we're doing is trying to find a way to track something in your body. So when we look at isotopes in the body, we're actually, in this case, using something known as technetium 99. Means nothing to you other than it's an isotope. In particular, we're looking at an isotope in this case that's looking at skeletal structures. So you see the bright areas, these very bright spaces, right? Okay, great, terrific. Bright spaces here, here, here. Why are these such bright areas? Well, if it's a tracer for skeleton, right, for skeletal compositions, we've got to look at the fact that it's going to light up the skeleton. Does it do that? Most certainly does. What about here? This is actually a PET image. Has nothing to do with your dog, but it's a PET image that's actually looking at plaque on the brain. So where you see these bright hot spots on this Alzheimer's patient compared to a normal healthy person's brain on the left, we look at high levels of plaque formations. And these plaque are indicative of Alzheimer's.